Hi there everyone, Mr. Pope from Grammar School for Boys, and today we're going to be looking at sketching graphs. Okay, couple of tips and tricks. First of all, whenever you're thinking about what a graph looks like, you should always consider, especially when you're dealing with the XY plane, substituting in points is always a good idea. Now, sometimes you can do that, sometimes it's not particularly defined at a point. For example, if I'm dividing by a factor and I let that factor equal to 0, dividing by 0 generally isn't particularly a good idea. Generally speaking, when you substitute in points, you can do that for 2 dimensions, 3 dimensions, as many dimensions as you like. You just have to take into consideration what is the space you're dealing with. For 2 dimensions in the xy plane, it's very simple. When x equals to 0, you are on the y-axis, and y equals to 0, then you are finding the x-axis intercepts. Okay, and that's probably like the key bit to it. There's a few other bits. For example, this is going to sound a little bit mental, but what's called the fundamental theorem of algebra. Okay, now I'm going to paraphrase it because there's lots of little intricacies to it, but essentially the fundamental theorem of algebra states that if I have a polynomial in x, okay, and this polynomial has a coefficient a0, a constant, plus a1, a different coefficient of x to the 1, plus a different polynomial, different coefficient a2 of x squared, plus a3 of x cubed, plus all the way up to an of x to the n. And we've got to have, well, I mean, essentially a1, a2, a3, and so on could be 0, but generally speaking, we want one of them not to be a 0. So at most, one of a1, a2 does not equal to 0. Then p of x equals to 0 has n complex roots. Okay, so what does that mean? Well, remember, complex is made up of real parts and imaginary parts. So let's take a really easy example of that. Let's suppose I've got a quadratic. Let's say I've got y equals x squared minus 2x plus 1. Okay, if I wanted to solve 0 equals x squared minus 2x plus 1, this is just x minus 1 all squared. So that means x is going to equal 1. And also x equals 1 as well is another solution. There are 2 roots here, they are repeated. Now, in this case, the imaginary part is 0. If I was to try y equals x squared plus x plus 1, then if I was to solve, well, let's go back to the original one. What does y equals x squared minus 2x plus 1 look like? It's going to bounce on the x-axis at 1, it's going to cross the y-axis at 1 as well, and it's going to be a U-shaped parabola like this. Okay, if I look at y equals x squared plus x plus 1, and maybe I complete the square, so it's x plus a half squared, minus a quarter plus 1 is plus 3/4. And then I'll minus 3/4 over to here, so I've got x plus a half all squared. And then I'll square root both sides to get the square root of negative 3 over 2, plus or minus that, and this equals x plus a half. And so x will equal minus 1 plus or minus root 3i over 2, where I is the square root of negative 1. And just out of curiosity, this graph will have a minimum at x equals minus a half and 3/4 on the y, and it's going to cut through the y-axis at 1. It's going to look like this. Okay, so this has two complex roots. It has minus 1 plus root 3i over 2 and minus 1 minus root 3i over 2. So in this case, they're complex in terms of they have a real and imaginary part. Here, x equals 1 and x equals 1, they're repeated and they're the same, they're not unique, and they're also complex, but the imaginary part is 0. I mean, every real number is a complex number, but not every complex number is a real number, right? Because there might be an imaginary part. If you're just dealing with A-level maths and not doing further maths, you don't need to worry about the imaginary part. But you still need to be able to draw graphs as shown. And then the final part, let's say I've got y equals x squared. Let's have x squared plus x minus 2. So if I set this equal to 0, I'll get 0 equals x squared plus x minus 2. And I believe that's x plus 2 times by x minus 1. So that's going to correspond to crossing the y-axis at 1. Sorry, the x-axis at 1, the x-axis is minus 2, and the y-axis at minus 2 like this. It's going to be a U-shaped parabola looking like this. They're all supposed to be the same shape, I'm just terrible at drawing. And this minimum here is when I complete the square on this, so x plus a half, all squared, minus a half, lots of squareds, minus a quarter, minus 2, I believe, is minus 9/4. So that point there is minus a half, because you set the bracket equal to 0 and solve for x. And the y-coordinate is just this m bit, which is minus 9/4. Okay, so I've shown you the case. They all have two complex roots. They all have two complex roots, as highlighted in orange. But in some cases, they're both real. Sometimes they're real and not unique, and sometimes they're both complex and they have imaginary parts. Okay, so what does this mean? Essentially, if I have a cubic, so what does this mean? It means if so what's the upshot of this? The upshot is if I have a cubic like y equals sum x cubed and so on, then at most I can have 3 roots or 3 x-axis intercepts. At most. At most. If I had y equals a x to the 4, then at most I could have 4 roots. If I had y a x to the 10, then at most I could have 10 and so on. This just is at most. It might not have any, it might have 1, it might have 2, it might have 7, it might have 6 and so on and so on. And generally speaking, whenever I have y equals, let's say, a constant of x to the odd power, and this odd power is the largest one, then you're going to get either, well, you're going to get a multitude of things. You're either going to get a straight line up, or like a kink like that, or maybe something like that with extra bits and so on. So if I just do a couple for you to illustrate what's going on. So let's say I've got something like y equals sum x plus b. Well, that would be a straight line looking like that. Let's suppose I've got some y equals ax cubed plus bx plus c, whoops, bx squared plus cx plus d. Then that might look like a cubic that we've seen before. Suppose I've got some y equals ax to the 5 plus bx to the 4 plus cx cubed plus dx squared plus ex plus f. Then this could potentially look like a cubic, but with even more bits in it, with even more twists and turns. And the reason why, the reason why is because look, from the orange one, it's a power of 1, so we can expect at most 1 intercept with the x-axis. With the red one, which is cubic, we can expect at least 1, well, at most 1, 2, 3 solutions. And when we've got to the power fifth one, we can expect at most 1, 2, 3, 4, 5 intersections with the x-axis. Now, it might not be any. For example, this graph might be shifted upwards like that, in which case it's only going to intersect at that bottom left one. You know, we just don't know. But at most, there's going to be 5 intersections. Now if I pull a similar trick, but this time with y equals some constant times x to an even power, what's going to happen there? Well, let's say I've got y equals ax to an even power. Okay, so same deal. Let's have y equals x to an even power. Let's start off with ax to the 0. Well, x to the 0 is even, and x to the 0 is just 1, so it's just going to be a horizontal flat line like so. Let's suppose I've got y equals ax squared plus bx plus c. Then this will probably look like a U-shaped parabola. If I have, let's say, y equals ax to the 4 plus bx cubed plus cx squared plus dx plus e, then this could potentially look like a U-shaped parabola with bits in the middle. And same logic here. X to the naught has no intersections with the x-axis, unless in a very special case when a equals 0. When we're dealing with the quadratic case, x squared, we could have at most 2 intersections. And then when we're dealing with the quartic case, x to the 4, we could have at most 1, 2, 3, 4. And it's a similar argument that I made with the odd functions, right? It's just a matter of a vertical, horizontal translation, which means you could have less than that, but you can never have more. Okay. So just simple polynomials you should be able to sketch, and there's no trick to this other than see if they factorize. Quadratics are a special case because you can complete the square, and this maxim up here of when x equals 0 you're on the y-axis and when y equals 0 you're on the x-axis is good as well. The other key point to sketching graphs, which is really, really helpful, and I think it's understated, is using the fact that dy by dx and set it equal to 0 to find maximums and minimum points. Okay, that is such a key skill. Okay, finding the derivative and using that fact to find maximum minimum points is really, really good. Okay, now there's a few other special case graphs you may need to consider. So for example, you may need to consider y equals 1 over x. Okay, and what does that look like? This is called a hyperbola, and it looks like this, and it has asymptotes, i.e. points where the function cannot take place when x equals 0, and a horizontal asymptote when y equals 0. And to give you a feeling of what's going on here, this hyperbola, as x tends to infinity, oops, that's an 8. When x tends to infinity, y is going to tend to 0. So if we start there, it's going to die off but never actually get to 0. And then similarly, as x tends to 0, then y tends to infinity from the positive side. So it's going to just shoot up like that, and it's going to hug the y-axis and so on. Now in the quadrant 3, by the way, this is quadrant 1, this is quadrant 2, this is quadrant 3, the third quadrant, this is quadrant 4. Wow, that's terrible. Quadrant 4 with Roman numerals. Then in the bottom left quadrant, it's the same thing. It's going to tend to minus infinity. As x tends to minus infinity, then then y is going to tend to 0 from the bottom. And okay, so let me write that down. So when x tends to infinity, y goes to 0 from the positive side, and as x tends to 0 from the negative side, y tends to negative infinity. And as x tends to negative infinity, y tends to 0 from the negative side. Now I've got minus as a power in 0. That just means 0 from the negative side. And this 0 plus just means 0 from the positive side. Like we're approaching 0, but we're coming at it from above. Whereas 0 minus just means we're approaching 0 from underneath. Another little factoid might be useful. Oh dear. Is, let's shrink this down. No, shrink. No, come on. Yeah. Another factoid that might be useful is the y equals 1 over x squared graph. It's going to look very similar, but this time it looks like this. It's not a hyperbola. It's just going to look like that. Well, this is the y-axis, this is the x-axis. And I should really label my axes in all fairness, but I'm too lazy. And same deal. It has an asymptote. An asymptote when x equals 0, and it has a horizontal asymptote as well when y equals to 0. Spotting asymptotes is really easy, because whenever you divide by something, you just let that thing equal to 0, and that tells you the equation of the asymptote. So here, x squared equals to 0, which is going to lead to x equaling to 0. And then finally, how would we find the horizontal asymptote? Well, if y equals 1 over something, this can never, y can never equal to 0, can it? Because the only way this can equal to 0 is if the top of the fraction is 0. And since it's 1, even if we let the bottom tend to infinity, it's still not going to be quite 0. So you have to be a little bit careful there. Okay, now the final thing I wanted to talk about is something called transformations. Right, this is really, really critical. Okay, that's very similar to what you've seen in GCSE. Let's suppose I call the function f of x. Okay, then the maxim I always use, especially for 2 dimensions, it's not quite the same in 3 dimensions, but you can kind of noodle it around, is whenever I do something inside the brackets, i.e. timesing by a number or adding a number, whatever, then this is an x directional change. It's not as expected and not using BODMAS or BIDMAS or PEDMAS, whatever you want to, or rather not using BODMAS or BODMAS, PEDMAS, whatever. The order of operations, BODMAS, is reversed. Okay, so that means when you're evaluating it, you would do the plus bit first and then you would scale it up or down. Okay, and similarly, and so I could have a minus there. Similarly, if I had my function f of x like so, but this time I was multiplying by a constant on the outside or a negative constant, for example, then adding something, then this is a y directional change as expected, and BODMAS is fine. It works the normal way. So you would do the multiplication bit first. You do the multiplication bit first and then you'd add stuff. So let me give you an example of what I mean by that. Let's suppose, so e.g., let's suppose I've got f of x equaling to x squared. So what does that look like? Here it is on my graph. It's a U-shaped parabola. It looks like this. There's my y, there's my x. If I were to do f of x plus 2, which means I've now got x plus 2 all squared, right? Notice how I'm replacing the input here, like so. Now, because this is inside the brackets, it's x directional, not as expected. So instead of adding 2 to the x direction, I'm actually going to move back 2. So it takes, oh dear, should have done it in 1. Let's do it in 1 so I can move it around. So this, like this. So if I take this, copy, paste, style, orange, right, okay. So it takes this graph and it's because it's inside the brackets, it's x direction not as expected. So instead of moving right 2, it's actually going to be moving left 2 on the x-axis. So I know immediately that if this was 0, then it's going to have a minimum here at x is minus 2, 0. Okay, now what about multiplication? Well, okay, let's suppose I had f of x minus 3, which means I'm going to have minus 3 lots of my function x squared. Okay, so what's going to happen there? Well, it's outside the brackets, so it's going to happen as expected, but this time in the y direction. So that means all of the y coordinates get multiplied by minus 3. So if this point here was, say, x was 2 and 2 squared is 4, then that 4 gets multiplied by minus 3, so it now becomes minus 12. So the corresponding point for the new graph is going to be 2, but minus 12 down here. So it's going to be 2 minus 12. And in actual fact, it's just going to be 3 times steeper, but reflected in the x-axis. So it's outside the brackets, so it's a y-directional change. So y-directional is up and down, so it's being reflected in the up and down direction, i.e. about the x-axis. Okay, it's really important. Generally speaking, multiplying by a negative number is a reflection. Multiplying in general is an enlargement. And adding or subtracting is a translation. Okay, if you can get your head around this kind of stuff, it's really easy. I'm just going to go through some examples. If you want to pause the video and give it a go yourself, that's absolutely fine. Just going to grab a drink. Okay, so the diagram above shows the sketch of the curve of the equation y equals f of x. The curve has a maximum point A at minus 2, 3, and a minimum point at 3, minus 5. On separate diagrams, sketch the curve of the equation y equals f of x plus 3. Okay, so what I'm going to do is I'm going to make a quick sketch of this. I'm just going to draw over it, like that. Oh, I can't trace for toffee. Okay, so I'm going to take this, and let's say I made my sketch like so. Let's make this smaller. Okay, f of x plus 3, it's inside the bracket, so it's x direction not as expected. So instead of adding 3, I've got to subtract 3 from all the x coordinates. Oh dear. So, so I take the curve and I go back 1, 2, 3, so it's now going to look like that. Okay, so this maximum here is now a minus 5, 3, because it has to go back 3 from minus 2. Oh, and this minimum actually should have been 3 minus 3, which is 0 minus 5. Okay, y equals 2 f of x. Well, that's going to look more or less the same. Oh dear. So what's going on here? It's going to be a y-directional change because it's outside the brackets and it's being multiplied by 2. So it's going to get twice as steep, still go through the same x-axis stuff, but this time this coordinate, the minus 2 is going to stay the same, but now this 3 is being multiplied by 2 to make a 6, and now this minus 5 is being multiplied by 2 to get 3 minus 10. On each diagram, show clearly the coordinates of the maximum turning point, minimum points. Yep, we've done that. Okay, the graph y equals f of x plus a has a minimum at 3, 0. What is the value of a? Well, a is clearly 5, because this minimum, 3 minus 5, needs to go up 5 amount of things, and outside of the brackets, of the f of x brackets, means y direction as expected. So that a needs to add 5 because the whole graph needs to be shifted up 5. Another way of looking at it is if I substitute 3 into f of x, I know this will output minus 5. And then if I add a, this is my y value. I want my y value to be 0, so I'm solving minus 5 plus a equals to 0. So what must a be? A must have the value of 5. There's multiple ways you can look at this. It doesn't particularly matter. That way I solved it algebraically. The other way I just considered graph transformations. But yeah. Okay, pause the video if you want. Have a go at this one. See if you're right. These questions are really nice because you can sketch them and solve them in seconds. So, on separate diagrams, sketch the curve. I'm just skipping all this stuff because usually this stuff is just said in the question 9 times out of 10. Diagram above shows a sketch of the curve. Yeah. The curve has a maximum point. Yep. And a y-tope bomb. Y of f of x plus 2. Okay, so it's going to have the same shape outside the brackets, y direction as expected. So it's going to go from there up like that. But now it has a y asymptote here. And instead of being at 1, it's now going to be y equals 3 because it's up 2. This is going to be minus 2, and then the 5 goes up 2 to a 7. And that's it. Y equals 4 f of x. Well, it's going to have a similar shape. So up like that. It's outside the bracket, so y direction as expected times by 4. So minus 2, the x stays the same. But now 5 times 4 will give a 20. The y asymptote here was y equals 1, but it's now going to be y equals 4 times that 1, which is 4. Then y equals f of x plus 1. Inside the bracket, x direction not as expected, so we need to go back 1. So this is going to be up, down, like that. The asymptote is still y equals 1, because that's just moved left, it hasn't changed. But now this maximum has still got a y value of 5, but it's now going to have an x value of minus 3, because the minus 2 needs to go back 1. Okay, on each diagram show clearly the coordinates of the maximum point and the equation of the asymptote. Okay. Right. On the same axes, sketch the graphs of the curves of the equation y equals x squared times x minus 2 and y equals x times 6 minus x. Okay, first of all, if I was to expand this, I would get x cubed minus 2x squared, which is a cubic, so I'm expecting it to look like that. X times 6 times x minus x plus x minus x is going to be 6x minus x squared. This is a negative quadratic. You take the highest power as the thing you compare, so that's going to be an n-shaped parabola. So immediately I'm looking for those two shapes. So if I draw a sketch of what's going on, I'm going to leave them in factorized form, and remember that when x equals 0, I'm on the y-axis. So when x is 0 for the first one, then 0 squared times 0 minus 2 is 0. And then for the second one, y equals 0 times 6 minus 0 is just 0 times 6, which is also 0. So I know they have those 2 points in common. Next up, when y equals 0, we're on the x-axis. So let's solve. 0 equals x squared times x minus 2, which means either x squared equals 0 or x minus 2 equals to 0, which gives x equals 2. So I know that for the cubic, it's going to cross x is 0 and x is 2. And if I mark this off with the orange pen, then because it is 0 twice, well, it has a root at 0 twice and a single root at 2, then I'm guessing it's going to look something. It's going to bounce at 0 and then cut through 2 like that. It's going to be a cubic looking like that. That was terrible. In actual fact, it's probably best to do it in one smooth go and draw the points in afterwards. Jesus. Wow. Sorry, my iPad's pretty slippery. Something like that. So there's 2, there's 0. Okay, now if I do a similar thing, but this time in red with x and that thing, you can clearly tell x is 0 and x is positive 6. So positive 6 is going to be way out to the right. So if 6 is over there, say, then it's going to be an n-shaped parabola that goes through 0 like that, comes down like so. It's going to cross the x-axis at 6. If we extend this x-axis out to there, maybe. Now we have a good sketch of what's going on. Indicate on your sketches the coordinates of the points where the curves cross the x-axis. Yep, I've done that. Use algebra to find the coordinates of the points where the graphs intersect. Well, straight away, I know one of those points there is 0, 0. They're going to intersect at the origin. The other point is this one up here. Now, the only thing I know about that is it's above 2 but less than 6. So let's try solving x squared times x minus 2 equals to x times 6 minus x. Now, ordinarily speaking, you never, ever, ever, you never divide by the variable or the function of the variable you're working with. Because when you do that, you may lose roots. So for example, it'd be really tempted to delete an x there and to delete an x there, i.e. divide by x both sides. And the only reason we do that is because if we divide by x, we're losing the x equals 0 solution. But that's okay because we've already considered it. Another point on this graph is this cubic is going to fall quicker than this quadratic is. So actually, it looks like there's going to be another point of intersection down here. So it looks like there's 3 points of intersection. One we've got taken care of, is 0, 0. The other 2 we need to find. So if we now solve x times x minus 2 equals to 6 minus x, we will get x squared minus 2x equals 6 minus x. If we add x to both sides, we'll get x squared minus x minus 6 equals to 0. I think that's going to be x minus 3 times by x plus 2 equals to 0. So either x equals positive 3 or x equals negative 2. So this point here must be where x is 3. And this point down here must be where x is negative 2. Whoops, not 0. And now we can just substitute in the y values to see what will happen. Well, I'm probably going to solve it into the quadratic because it's easier. So when x is minus 2, I've got minus 2 lots of 6 minus minus 2, which is 6 plus 2, which is 8. So that's going to be minus 16. And then if I sub 3 into the quadratic, I've got 3 lots of 6 minus 3, which is 3. 3 times 3 is 9. So my two answers are 3, 9, minus 2 minus 16, and actually I can't forget the third answer, 0, 0. So those are my final answers, 3, 9, 0, 0, and minus 2 minus 16. Okay. Right. So just to throw a little bit of a hard one in the mix, I've given a part A of a step questions. This is quite difficult. You've got all the things you need to know how to solve this kind of thing. So pause the video, give yourself a go. I'll go through it shortly. Okay, right. So I want to sketch this function. So generally speaking, when I want to sketch functions, I want to consider dy by dx equal to 0 is where maximum and minimum are, and I want to know that when x is 0, we're on the y-axis, and when y equals 0, we're on the x-axis. Okay, so let's do the easy ones then. X is 0, y, they're on the y-axis. So what does y equal? So when x tends to 0, what is y? Well, we're going to have 0 squared, which is 0, e to the minus 0, which is 1. So you've got 0 times 1, which is 0 on the top, over 1 plus 0, which is 1, and 0 divided by 1 is 0. So I know straight away, as a gimme, that my function I'm trying to solve here crosses through the origin 0, 0. 100%. Okay, what about when y equals to 0? So what happens when y equals to 0, i.e. 0 equals x squared e to the minus x all over 1 plus x? Okay, so first of all, a fraction can only equal to 0 if the top part equals to 0. right? So if somebody said how many sixths equals to 0, then okay, let's make that an x. Then if I times the 6 over, then I just have x equal to 0. The only way a fraction can equal 0 is if the top equals to 0. So essentially this is saying x squared times e to the minus x equals 0. When is that 0? Well, it'll either be when x squared equals to 0 or when e to the minus x equal to 0 because they're factors. X squared equals to 0 just gives x equals to 0. That's boring, we've already got that one. E to the minus x is a bit tricky because e to the minus x is an exponential decay. Now think about it. E to the x, right, is the exponential graph which you've seen before, which rises like that. Now if I put a minus x in there, then that's the same of f of minus x, which is a reflection in the x direction, not as expected. So reflection in the x direction means it's now going to be declining like this. So from left to right, it's actually going down and hugging. The point is it never crosses the x-axis, so this has no solutions. If you want, you can try logging both sides to get minus x equals log of 0. If you try log of 0, your calculator's going to be like, can't deal with it, what's going on? And the reason for that is because the negative exponential graph never actually crosses the x-axis. It doesn't have a value for an output of 0. Okay, so it looks like the only time this function, to be fair, this is great. Now you're probably thinking like, oh man, but we've only found one thing. Well, that's great actually. That means this graph either lives up here, up here, up here, up here, and it never crosses the axes at any points other than what we've said. So actually that's quite useful. We know that 0, 0 is a point on the graph. That's it. Okay, now we're going to utilise this dy by dx equals to 0. So now we're going to differentiate x squared times e to the minus x all over 1 plus x. Now we've done enough calculus to realise that this is a quotient rule problem, i.e. to do the quotient rule, i.e. u over v, and we want to differentiate that, that is going to be v du, differentiate u, minus u, differentiate v, all over v squared. And we can compute this quite easily. So let's do it in stages so we don't mess up, because it would be a shame to mess up at this stage. So u is x squared times by e to the minus x, and u dashed, which is the differentiation of that. Well, this is a product, so we need to differentiate one at a time and add those combinations. So differentiate x squared becomes 2x times by leave e to the minus x alone, plus leave the x squared alone, and now differentiate e to the minus x, and by the chain rule, the minus comes out to the front, so this is minus e to the minus x. If you tidy all this up, this means u dashed equals, well, what do these two terms have in common? They've got x e to the minus x in common. The first term is just 2 lots of that, and the next term is minus x lots of that. So we've got u dashed, we've got u, and then v is just 1 plus x, so that's easy, that's given, and v dash is just the differentiation of 1 plus x, which is just 1. So now we're ready to rock and roll. So this is going to be v du, so we've got x e to the minus x times by 2 minus x times by v, which is 1 plus x, minus u dv, which is just 1 times that thing, so it's going to be x squared, lots of e to the minus x, and this is all over 1 plus v squared, v, which is v squared, which is 1 plus x, all squared. Now the great thing is, if we want this to equal to 0, then as before, we only want the top part of the fraction to equal to 0. Same deal. You can see that x e to the minus x and x e to the minus x are factors here. So x times e to the minus x is a factor of, now the first term you just times by this quadratic, which is 2 minus x times by 1 plus x. And then clearly x squared times e to the minus x is going to be minus x lots of x e to the minus x. So this is actually minus x lots here, and that equals to 0. Okay, so couple of things. Either x equals to 0, which is nice, That's okay. Or e to the minus x equals to 0, which can't happen. Or this stuff equals to 0. And let's expand it and see what happens. So 2 times 1, which is 2, minus x times 1, which is minus x, 2 times x is plus 2x, x times minus x is minus x squared, and I've got a minus x on the end. Minus x plus 2x cancels, so that must mean 2 minus x squared equals to 0, which means x equals positive or negative root 2. Aha! Now this means that we have 3 turning points, one at 0, one at root 2, and one at negative root 2. So there's going to be something interesting happening at root 2, there's going to be something interesting happening at minus root 2. And then to find out what's going on here, this is relatively easy, because all I have to do is substitute those values in. Now here's the great thing, I don't even need to know what those values are, I just need to know if they're positive or negative to tell whether they're above or below the x-axis. So, root 2 squared, that's positive. E to the minus root 2, that's positive again. 1 plus root 2, that's positive. So I know it's going to be some point up here. I know it goes through 0, 0, and it goes to that point, and that's a turning point. So if it's gone from low to high, this must be a maximum. There's no doubting of it there. Well, is there? We need to backtrack a little bit. And the reason for that is because we're dividing a fraction here. So look at the bottom. Can we divide by 0? I.e., what must 1 plus x be to equal to 0 to make rise to this not being possible? Well, if 1 plus x is 0, x equals minus 1. So I now have an asymptote where this function does not exist when x equals to minus 1. So there's like this barrier where this function is disjointed. So when x equals to minus 1, a function doesn't exist. And that's the only place the function doesn't exist. So actually, yes, we were justified. Okay, next up, if 0, 0 is a turning point, think about it logically. Could that also be a maximum? Could it? Well, think about it. If it was a maximum, that means the graph's going downwards, and the graph around root 2 going to the left is going downwards again. Now see the contradiction here. If it's going downwards, it must cross the x-axis at some point to meet it down here. And there must be a minimum down here for these two things to meet. Now there's two contradictions here. We've already proven that it doesn't cross the x-axis again, so that can't be right. And we've also proven that there's three turning points, and 0, 0 is one of them. So it doesn't make sense for 0, 0 to be a maximum. In actual fact, it must be, in that case, a minimum. And that seems to make sense because then that joins up like that, and that's fine. Next up, if this is a maximum, how can that be the case that it goes down like that? It doesn't cross the x-axis anymore. So what must it do so it no longer has any maximums again? Well, it must die off and never quite reach x again. How do I know that's the case? Because let's think about it. What were to happen if x would go to infinity? Then x squared would be infinity. E to the minus x, well, let's think about that. E to the minus x when x is infinity is just e to the minus infinity, and that tends to 0. And 1 plus x on the bottom, that will just tend to infinity. Well, what's going to happen here? E to the minus x goes to 0 quicker than x squared blows up. So 0 is going to be the dominant thing here. Okay, exponentials always beat the powers. We'll talk about that more when we look at limits of convergence and stuff like that. 0 is going to be the main leading term here, and similarly this is a linear term on the bottom, so this x squared would have been... Well, I'll tell you what, here's a cheeky trick. Let's say I've got x squared over there, and I've got e to the minus x over there like that, and I've got 1 plus x on the bottom here. Let's suppose I divide by x top and bottom. So this becomes x e to the minus x. On the bottom, I've got 1 over x plus 1. Well, we can pull this trick again. We can divide by x top and bottom as well. So we've got 1 times e to the minus x over 1 over x divided by x again is 1 over x squared plus, and then we've got a 1 over x. Now these three things are all identical. Now look what happens as x tends to infinity. I've got 1 over infinity squared, so that's going to tend to 0, plus 1 over infinity, that's also going to tend to 0, and on the top I've got 1 times e to the minus infinity, which is also 0. This is indeterminate. We don't know how to deal with this. If I look over to here though, I've got 1, if we look over to this one, I've got 1 over x, where x goes to infinity, so that goes to a 0, plus 1, so it's all over 1, so at least that's dealt with. But now I've got x tends to infinity, but e to the minus x is e to the negative infinity. Well, what does the y equals x graph look like? Y equals x graph looks like this, doesn't it? It's linear. And the minus e, and then e to the minus x graph is the exponential decay, which swoops down like this. So logical question, does this graph tend to 0 quicker than this line tends to infinity? Well, I'm hoping you can see that this graph down here, the e to the minus x graph, tends to 0 incredibly quickly, whereas this graph, the y equals x graph, will get to infinity, but it's just chugging along fairly slowly. So we'd say, in a nutshell, this term dominates, and the e to the minus infinity is 0, so this whole thing can be evaluated at 0, which means as x tends to infinity, this thing tends to 0, and yeah, we're going to have something looking like that. Yeah. Right. Now a similar argument can be made with what's going on here. As x tends to minus 1 from the other side, this is going to scoot up to positive infinity like that. Now what we've got to do is figure out what's going on the left-hand side. So let's deal with this. If I substitute in minus root 2, then minus root 2 squared is positive. E to the minus root 2 is e to the root 2, which is positive again. But now 1 plus minus root 2, which is 1 minus root 2, since root 2 is bigger than 1, then the bottom becomes negative. So positive times positive divided by negative is negative, so it's going to be down here. I know this graph... Okay, so do we have a maximum or minimum? Well, if it was a minimum, then because there's nowhere for it to go to the right, then if it were going like this, it would have to keep going to infinity like that. And the problem with that is that argument means it crosses the x-axis, and that can't happen. So unfortunately, it being a minimum just won't be the case. So this has to be a maximum, where this tends to negative infinity like that. And now, because this can't go up and hug the x-axis, it looks like this is just going to skewer off down there like so. If you want to prove that this is actually a maximum, then you find the second derivative, which you can do for yourself, and prove that this is negative for when you substitute in x equals minus root 2. And similarly, if you want to prove that this is a maximum, then you find the second derivative and show that that's negative for when x equals negative root 2. And then if you want to prove this is a minimum, you find the second derivative, show that it's positive. So positive when x equals 0. And yeah, so my graph, I think the graph is going to look like this. And if you use Desmos or Wolfram Alpha, I'm pretty sure you'll find I'm right. So there's going to be that x equals minus 1, which the graph doesn't exist for. It spikes off to positive infinity from the right-hand side of that graph. It spikes off to negative infinity from the left-hand side. You've got this weird N shape to the left of that discontinuity, and to the right you've kind of got this little bump at root 2, and then the function dies off again. Yeah, this was part of a step question. The second part was you were asked to evaluate this integral, or rather the area of this function between here and here, i.e. integrate between 1 and 0 x squared e to the minus x over 1 plus x dx, and show that it lies between 0 and 1. It's fairly simple to do, but you'll need to know integration by parts, and we haven't covered that yet, so that's why I've omitted it. But it's fairly easy to do. And if you want to hold on to this question and try it again later, then by all means do that. Okay, last question. Show that this thing can be written as that. Okay, well, all I'm going to do is I'm just going to multiply out the right hand side. So x times x is x squared, x times the y is plus xy, x times the 1 is minus x, and now minus y times the x is minus xy, minus y times y is minus y squared, minus y times minus 1 equals plus y, and then two lots of all this stuff is plus 2x plus 2y minus 2. You can see the xy's cancel. I've got a minus x there and a plus 2x there, so that's going to give a plus x. I've got an x squared and a minus y squared, so x squared minus y squared is there. And I've got a plus y and a plus 2y, which is plus 3y, and then that's minus 2. And I believe this is the same as what we're trying to show here. So that's fine, they are the same. Hence or otherwise indicate by means of a sketch the region of the xy plane for which that is greater than 2. Okay, well, if I minus the 2 from the other side, it's asking me to do x squared minus y squared plus x plus 3y minus 2 is greater than 0. And I've already got it in factorised form, so I'm probably going to consider that first. So let's consider x minus y plus 2, and this is x plus y minus 1 is greater than 0. By the way, this question is another step question. Don't feel too bad if you can't do these just yet, but just be aware that these questions do exist. They're not part of the A-level course, but just working through them is just great for your overall understanding. Right, now we've got some rather nasty looking inequalities here, but we're going to use our knowledge of graph sketching to solve this. Now, if I've got, essentially, why have we done this? Because I've got a quantity times a quantity is greater than 0. So that means either both of them are positive or both of them are negative. And we have to consider both cases. So what I'm going to do is I'm going to draw a sketch of each one first. So the critical region. So let's think about that. So let's call this 1. Let's call this 2. So for 1, let's consider x minus y plus 2 equals to 0. So if I add y to both sides, this means y equals x plus 2, and I know what that thing looks like on a graph. So if I draw, there's my graph, y equals x plus 2 is going to be a line, gradient 1, looking like that, crosses the x-axis at minus 2, the y-axis at 2, and that's done. Okay, if I now consider graph 2, which is x plus y minus 1 equals 0. If I get everything to the other side, so y equals minus x plus 1, then that's a gradient of minus 1. It crosses the x-axis at 1. No, the y-axis at 1, and it's got a gradient of minus 1, so it's going to be perpendicular. It's going to look like that. So it's perpendicular. It's not, I don't think that's particularly relevant at this point. And we could work out this point of intersection here. So if we set the x plus 2 equal to minus x plus 1, then this becomes, if we add x to both sides, that's 2x minus the 2 from both sides minus 1. So x appears to be minus half. So if x is minus half, then I believe the y becomes 3/2. Yeah, because if I substitute it into this one, 2 minus a half is 3/2. Okay, fine. Okay, So let's consider, right, now please note how I've done this, right? I've kept the position and orientation of these the same. So that now, if I want to know where this thing is positive, then x plus 2, which is positive y, is what I need to consider. And I also need to consider y positive minus x plus 1. Okay, yeah, because if I set this thing, x minus y plus 2 is positive, can you see how I'd add that y over to that side? I've conserved it. Okay, so the orientation in this step is quite important, I feel. Anyway, so which region is y is less than x plus 2, so that's below the x plus 2 line. So what's below this line, but y greater than x minus 1, but above this line? Can you see the region that corresponds to? It's actually going to be this region here. Everything there is below the line with positive gradient, but above the line with negative gradient. And then similarly, if I consider the negative case where they're both negative, i.e. x plus 2 is less than y, and y is less than minus x plus 1, you can see that it's just a flip of that. What's the region that's below? What's the region that's above the positive gradient, and what's the region that y is lower than the negative gradient? That's clearly this bit here. So you've got some weird, if you remember those toys called Diablos, those weird cone, those weird hyperboloid shapes. Okay, so those are the two regions. Just get them shaded in a little bit better. Okay, so any coordinates in here should satisfy that. And just to check, maybe we should. This point here was, it was 1, wasn't it? Yeah, because we're on this line. So, I don't know, let's substitute in a point. Let's go to over here, which is 2, 0. Does 2, 0 work? Well, when x is 2, then 2 squared is 4, minus 0 squared, which is 0, plus x, which is 2, plus 3 lots of 0, minus 2. Is that greater than 0? 2 minus 2, that disappears. 4 is greater than 0, that works out. Let's suppose I pick this point here, which is minus 1, 0. Does that work? Let's check. That shouldn't work because it's not in the region. So when x is minus 1, so minus 1 squared is 1, minus 0 squared, plus an x, which is minus 1, plus 3y, which is nothing, minus 2, is that greater than 0? Well, the 1 and minus 1 cancel. Minus 2 is not greater than 0. Yeah, that works. Okay, so after checking a couple of points, I'm pretty sure this is a correct answer, and I'm happy with what's going on so far. Okay, sketch also the region of the xy plane for which that is the case. Okay, so what that's so similar kind of thing, but now I want x squared minus 4y squared plus 3x minus 2y, and if I add the 2y over, that becomes plus 2, not minus 2y, and then that's less than 0. So a couple of things going on here. Right, can we intuitively do this? Well, okay, first of all, I spot that this is a 4y squared, and there's like a difference of squares thing going on here. So I suspect it's going to be x minus 2y times by x plus 2y. So it matches what's going on up here in the original question. And then finally, I know that the number terms at the end is plus 2. So either they're minus 1 minus 2, or they're plus 1 plus 2, or a switch. So there's 4 combinations there, which is a bit annoying. Okay. Does it matter? Well, a little bit actually, because I want minus 2y. So if I have minus 2y, and then add a 2 there, then that minus 2y times that 2 will be a minus 4y. And then if I have a plus 1 there, 2y times 1 will be plus 2y. So minus 4y plus 2y is minus... Yes, so that will work for that thing. Let's just double check the x's come out okay. X times 2 is 2x, x times 1, the x's are fine. X times x squared minus 2y times minus 2y is okay, so the x squareds and y squareds are fine. And then for the xy's, I've got x times 2y and minus 2y times x, so they disappear completely. That's fantastic. And now I want this to be less than 0. Okay, so same deal. I'm going to do x minus 2y plus 1 equals to 0, which means 2y equals to x plus 1. Keep the order, so y equals a half x plus a half. So quick sketch. So half x plus a half, it's going to be looking something like this, where it's going to cross the y-axis at half and the x-axis at minus 1. And then for this one over here, I've got x plus 2y plus 2 equals to 0, so 2y equals minus x minus 2. Divide by 2, y equals minus a half x minus 1. So minus 1 is down here. It's going to have a gradient of minus half, so it's not quite perpendicular to the previous one. It's going to be looking like that. Is it really? Yeah, okay. When y is 0, that's minus 2, isn't it? Okay, what's the point of intersection? So if I add a half x to both sides, then x plus a half equals to minus 1. If I minus a half, then x equals minus 3 halves. That should have been obvious, actually. So minus 3 halves. And then what's the y value? The y value is... half of minus 3 halves is minus 3 quarters. Plus a half is going to be minus a quarter. Okay, similar check. But this time, because I want it to be less than 0, then either this one's positive and this one's negative, or this one is negative and this one's positive. So in the case where the first one's positive, I've got the y, or I've got it positive, so I would have x minus 2y plus 1 is greater than 0, which tidies up to y is less than x over 2 plus a half, so where that's below the line. And then when the second one's negative, that's going to be x plus 2y plus 2 is less than 0, which will give y is less than minus a half x minus 1. So where is it lower than both lines? It's here. It's this bit down here. Then clearly flipping the inequalities for when one's negative, one's positive, is going to be y is greater than a half x plus a half, and the other one is y is greater than minus a half x minus 1, and that's clearly going to correspond to this upwards bit here. So that wasn't too bad, actually. Much of the same, you just had to spot the factorizations. That was actually incredibly easy. Yeah, not bad. Okay, so sketch also the region of the xy plane for which that's true. Yep, done that. Yes. Give the coordinates of a point for which both inequalities are satisfied, or explain why no such point exists. Okay. Right, so I could superimpose them, but I've got a funny feeling that I can find one quite easily. Let's say a point on the y-axis. Well, let's pick x is 3 halves. Sorry, that point there, where x equals 0 and y equals 3 halves. That's clearly a point on it. I believe so. So does this satisfy both things? Let's go up here. So when x is 0. Well, that's quite an easy one to check, actually. Let's go back up here. Let's do a different colour. So when x is 0, what happens? Well, that goes, that goes, that goes, and that goes. And when y is 3 halves, then minus 3 halves squared is minus 9 over 4, plus 3 halves, that becomes 9 halves. Is that greater than 2? Well, 9 halves minus 9 quarters is just 9 quarters. And is 9 quarters greater than 2? Yes, it is, because 9 quarters is 2 1/4, so that works. Let's go over here. 3 halves squared is 9 quarters. 9 quarters times minus 4 is just going to be minus 9. Minus 2 lots of 3 halves is going to be minus 3. Is that less than minus 2? Lol, that's minus 12 is less than minus 2, so that works. So yeah, there is actually quite a lot of points for which this is true. I found one just by looking at it, and that's where x is 0, y equals 3 halves. There's so many other ones as well. You could draw them on top of each other and solve, but that's a fairly straightforward one. Anyway, hope you enjoyed that. Graph transformations, pretty easy. Just wanted to show you some more difficult ones. Have fun.